Hey everyone, welcome back to the channel, and we're going to be continuing our DP-700 exam preparation course, and we've got a very special one for you today because we're going to be tackling real-time streaming systems. We're going to be looking at Eventstreams, Spark structured streaming, KQL, and patterns and all this kind of good stuff. Enough of the talking, let's dive straight into it. All right, so let's start with an introduction to real-time systems, because in data analytics broadly, there's two big paradigms. We have batch processing and we have real-time systems. Batch processing is the things that you're probably used to working in Fabric. So things like the data pipeline on schedules, they're getting batches of data from source systems, bringing them in, transforming them and visualizing them and all that good stuff. Data flows as well. So everything we've looked at in this course, and actually probably all I've ever talked about on the channel to this date, has been batch processing. So the characteristics are things like historical analysis. You're doing analysis of batches of things that have happened in the past. And normally there's some lag between data collection and then ingestion into your analysis environment, in our case, Fabric. Now, for most businesses and most use cases within those businesses, batch processing is sufficient for the running of their business. You know, when we talk about batch processing, you can still run batch processing on a schedule of every 5 minutes, for example. That's still batch processing, and that is more than enough for most use cases. But for some industries and some use cases within those industries, the development of real-time systems is worth the cost of implementing those systems. We'll talk about the cost of developing some of these shortly. All right, so let's explore some of the industries and the use cases that make sense for real-time systems. And the first big bucket that I would describe or group some of these use cases in is cyber physical, right? Where there's some sensors out there in the real world giving us data, streaming data into a platform. So things like logistics companies, transportation companies, more broadly IoT companies. Farming and agriculture is also increasingly becoming interested and invested in real-time systems. Then you have digital applications, right? So it's not necessarily sensors out in the field somewhere in the real world, but applications, digital applications that log data into real-time systems. So like financial applications, fraud detection, cybersecurity is a really big one, especially in the KQL community. Azure Data Explorer, which is where the KQL engine that we're going to be looking at later today comes from. You know, there's a reason why it's in Fabric, because, you know, it's been used for logging and cybersecurity and these kind of applications that are all real-time in the past. And finally, you've got things like big tech, right? So they're really driving forward and they use a lot of real-time systems, things like Netflix, Uber, Airbnb on their websites to optimize like click-through rates and things like this in real time. Yeah, I just want to highlight this point down here before we move on about real-time systems require a different data infrastructure, right? So completely different, sometimes physical infrastructure out in the real world. So sensors, definitely data infrastructure. You have to ingest things. You know, ingesting data into a platform 24/7 changes your infrastructure requirements. It also changes how you analyze that data and how you make decisions on that data as well, right? It's a completely different set of analysis principles and a different mindset in general, right? So I just wanted to frame out an introduction to real-time systems before we moved into the Fabric side of things and the DP-700 side of things, because this is the first time that we've looked at real-time systems on the channel. So with that, where are we with real-time in Microsoft Fabric? Because you've probably heard quite a lot about all the different KQL Database, Eventhouse, Activator, all this stuff. It's changed quite a lot in the last year, at least. So let's just map out what we have available to us and how they all relate in Microsoft Fabric. So the first thing that I wanted to lay down was batch processing, right? So that's all of our existing things like data pipelines, data flows, they still exist. And if you're doing batch processing, you know, I just wanted to create a bucket for those batch processing tools there. Then we've got this really big bucket of real-time processing tools. Now, what many people forget is that we have access to Spark in Fabric, and part of the Spark framework is structured streaming. Therefore, in Fabric, we can make use of this. We can ingest streams of data into your Spark cluster and then do transformations on it and perform whatever you would normally if you're using Spark structured streaming. You can do that within Fabric as well, no problem. If you're migrating structured streaming code from other data platforms, you can do that, no problem at all. And we'll look at that in more detail a little bit later on. But then we have the Fabric-specific tools. For ingestion, we have the event stream, which allows us to ingest data from a variety of different sources, perform a few different operations or transformations on that stream as it's incoming, and then write to a number of different destinations within Fabric or a custom endpoint as well. Then we have the storage side of things in the real-time area, and most of it is based around the Eventhouse, which holds one or more KQL databases. And we'll be having a look at those a little bit later on in this video as well. And then we have the analysis piece, right? So once you've got some data in your KQL databases, you can create Kusto Query Language queries to analyze that data. You can also build real-time dashboards from that data and from those queries as well. That's its own item, separate from Power BI. And then underpinning all of these, we have things like alerting, monitoring, and optimizations. Now, these are important to understand for the DP-700 exam, but they're not going to be the focus of this specific video. We're going to be looking at everything else on this picture, at least in the real-time section. Right, so we're going to look at a little bit at Spark structured streaming. We're going to do a deep dive on event streams and what they are and how to use them. Then we're going to go into the KQL databases and look at a wide variety of KQL queries that you need to understand for this exam. So with that said, let's dive into event streams first. Okay, I just want to start with a slide or two just to frame out event streams and what's available to us, and then we're going to jump into Fabric and have a look at some examples of these event streams just so you can put the theory together with the practical. Starting with the sources. So which sources can we ingest data from into our event streams in Microsoft Fabric? Well, the first group of sources, I would say, are the Azure real-time platform as a service solutions. So here I'm talking about Azure Event Hub, Azure IoT Hub, for example. So if you've already got, your infrastructure set up in Azure to ingest streams of data from the outside world, wherever they're coming from, then it's really easy just to integrate and send streams from your Event Hub into an event stream for some sort of analysis or visualization in Fabric. The other group of sources that I would highlight here are cloud databases that have change data capture enabled, right? So you can stream data from Azure SQL databases, Azure Cosmos DB, and I'm not showing all of these. There's more sources than this. This is just a flavor of them. But you can stream live updates from those databases directly into your event stream in Fabric. There's also the ability to stream data from Kafka or other third-party streaming platforms like Google PubSub or Amazon Kinesis as well, I think is another supported third-party platform that you can stream from into an event stream. Plus, also, we have Fabric and Azure event triggers. We looked at this in one of the earlier videos where we talked about triggers in Microsoft Fabric, and you can trigger an event stream from things like update to a OneLake folder or file or workspace events. So these are the type of the triggers that I'm talking about here. So you can stream those events into an event stream also. We also have custom endpoints. So if you want to ingest data directly from a device in wherever you're streaming from directly into an endpoint of a event stream, that is also possible. So they'll give you an address that you can fire events straight into if you don't want to use Azure Event Hubs or you don't have access to Azure Event Hubs already. That's another great option for you there. Particularly useful if you're building your own web application, for example, and you want to stream some logs directly into an event stream. You don't want to have to set up Azure Event Hubs. You just want to use event streams as your destination in some respects. And there's also some sample data, and some of the examples that we're going to be looking at are going to include that sample data so that you can play along at home and use the same data sets really easily. So let's look at some of the operations that you can perform on these incoming streams now. So these are the supported operations or transformations that we can perform on an incoming stream in the event stream. So once you've got some data from one of these sources, next you might want to perform some sort of transformation. This is optional. You don't have to. You can also do direct ingestion, where you're ingesting events directly from the source and you're writing it out to a destination. But if you want to perform transformation, you can with any of these. So let's quickly walk through what these are. So aggregation means you're performing some sort of aggregate on the data over a specified time window, so every minute, for example. But crucially, you're calculating this every new data point that comes into, or every new event that comes into the system. So it's quite an aggressive transformation, right? You're calculating a lot of data on every new event. Now, group by is a similar transformation to aggregate, but you're defining the window duration and the window length in some instances as well, and performing your aggregation over that window, not necessarily every time new data comes in, but over a pre-agreed window size. We'll look in more detail about group by and windowing in the next slide. So expand is fairly straightforward. Simply, we can expand a list of data, an array of values in a particular property in incoming data, and we can expand those into different data points on different rows in the output table. Filter, again, fairly straightforward. As you'd expect, you can filter streams of data based on some sort of rule. Join means we can join two streams together as they're coming in on a matching key, right? Similar to a join in T-SQL. And union is similar as well in that regard, in that, if you have two streams that have the same schema, that's going to join them vertically rather than on a matching key. Just going to put one on top of the other. Manage fields, last but definitely not least, perhaps the most important one. We can use manage fields to reduce the number of columns that you want returned, and secondly, change the data types, right? So that's very, very important. If you're getting data streaming in as JSON and you want to convert the data types to something more usable and write them into a KQL database in the right types, then you're definitely going to be wanting to use a manage fields. So once you've done all of your transformation and you've got your stream into the shape that you want it, these are the supported destinations, right? Number one is the custom endpoint. So it's not just as a source, we can use the custom endpoint, but we can also direct our stream back to a custom endpoint of your own, right? You have to own that custom endpoint. So it could be sending it back into a custom application that you've developed. Then we've got these fabric data stores, the Lakehouse or the Eventhouse. We'll look at the Eventhouse in a bit more detail later on. So just know that you can stream into the Lakehouse or the Eventhouse or both. Right, you can split your stream and write to multiple different destinations. Stream is an interesting one, which essentially means you can join two streams together. The output of one of your streams can turn into the input of another one of your event streams, right? So this is what's called a derived stream. And then we have activator. So if you want to set up alerting on your stream with some sort of condition, alert me when the data goes above this certain value, for example, that's what you do with activator. All right, so that's just the wide map of everything that's available in an event stream. Let's put this into practice and have a look at the UI and see what all this looks like. Okay, so here we are in an event stream, and it's what I would call a fairly basic event stream, right? So what I'm going to do is explain some of the key components, how it's put together, talk about the sources, the transformations, and the destinations available to you, as well as you getting accustomed to the layout of an event stream. So in this event stream, I'm currently in edit mode, right? So there's two different modes, edit mode and live mode. So obviously when you publish your event stream, when you're happy with it, then it's going to switch over to live mode, and then you can either ingest data, you can have the ingestion on or off once it's in live mode as well. But we're in edit mode because we want to investigate what's going on in this event stream. Okay, let's start at the left-hand side because this is a directed acyclic graph. So we're starting at the left and our event stream is going towards the right. So the source for my event stream is one of the sample data sets. So if you want to play along at home, you can grab the bicycles sample data as your source and follow along with us. Now the bicycles data set, if we just scroll up a bit here, what it's going to do is it's going to show you a preview of the data at each of the nodes in your event stream, right? So this is what the data looks like. This data comes from, I believe, London bike sharing schemes. So you have a bike point ID, which is like the station that different bikes are stored at. We have the street, the neighborhood, latitude and longitude. So we can do some geographical analysis on this if we want. And the number of bikes, and if we scroll to the right, we've also got a number of empty docks. Right? So if you imagine a station of bikes in a bike sharing scheme, you might have 20 docks. And currently, at the time the event was ingested, there are 12 bikes in this particular bike point currently and 6 empty docks. So in total, there'll be 18 at this particular bike point ID. Now, directly after your source node, you'll see this, which is kind of like the root node of our event stream. It's telling you the name of my event stream, RTO3, bike stream, which is what I've called it. It's the same as it is up here, right? And then everything after this node is where you can do your transformations and your destinations. In my example, this is what we've got, okay? So I've got two different routes for this event stream. Let's start with the top one first, right? So the top one goes all the way from basically our source into what's called direct ingestion, okay? So this is a destination node, and it's got this type called direct ingestion. Essentially, if you don't want to do anything, you just want to write the raw stream into a destination, you can do that. So we specify direct ingestion. We give the workspace name, the event house name. In this example, I'm direct ingesting into a event house, and we give it the name of the KQL database, and we just go straight into it. So that's my first destination for this event stream. Then along the bottom route of this event stream, we've got a manage fields. So typically you'll see a manage fields node directly after the source because the manage field node is really useful. We're using it here to select only a few different fields. So if we click into this and edit this manage fields, it's going to give us this dialog over here. We can add fields or add all of the fields, which means, the fields from our source. I think we had about 6 or 7 different columns. I've just chosen a few of them here. I've also added the current underscore time, which is kind of like the system time, right? So in this manage fields, what I've got is I've got 3 fields from the JSON file, the incoming JSON file, and I've also added this current time field, which comes from system.timestamp here. This is one of the built-in datetime functions. So this is essentially the time the ingestion takes place, system timestamp at that time, and I want that as a column in my data set for whatever reason. Then I'm also getting the bike point ID, the number of bikes, and the number of empty docks, right? Maybe I don't care about the latitude and the longitude. Maybe I'm going to get that from some sort of reference table, because these bike points are not going to move around, right? That's not really required. One thing you've got to bear in mind with streaming data is that sometimes it's very, very big data, right? So small changes you make in the structure of your stream here, you want to be as economical as possible, right? So you don't really want to be streaming 6 columns of data when you only really need 4 columns of data, right? Because over time that could be a billion rows and lots of data that you're storing for no real benefit. On the flip side of that, I would say that it's very, very important to think carefully about what you throw out at this stage, right? Just because you don't need a certain field now, well, I would recommend always storing it. Data storage is very cheap these days. And speaking as an ex-data scientist, I recommend keeping any variables that you have, even if you don't think they'll be useful right now, because they might be in the future. So let's just explore some of these other fields. So we've got the bike point ID, which is coming directly from the source. We don't have to change the type here. If you wanted to, that's where you'll change the data type in there. Number of bikes is the same. That's already coming in. I don't know if you can see that, but there it's like an integer number there already. So we don't need to change the type there. In the next example, we'll look at some where we do need to change the types. And number of docks. Again, number of empty docks. We don't need to change the type there. We can also rename it if we don't like the name of it, but I'm happy with that name. Then, as the next node in my event stream, I've added a filter. This time we're filtering on the number of bikes where the value is equal to 0, right? So we want to know when there's empty bike stations in this data set, because maybe we want to trigger some sort of process that goes to send bikes to that location. Or maybe we've got an app and we want to alert our users not to try to go to those locations to pick up a new bike because there's none there. Then after we've filtered the data in that event stream, we're going to write the output into this KQL table called empty racks. So we've specified the destination here. It's in this workspace, in this event house, in this KQL database, and in this table here called empty racks. So there's 2 ways that you can do this. Either you can create a KQL table beforehand and then stream directly into it, assuming you've got the same schema, the schema is matching up correctly, or when you're creating and authoring your event stream for the first time, you can use this create new, to generate a table in your KQL database and then stream directly into it. Now, once I'm happy with my event stream, I can switch it back to live mode, and then I can activate everything in here. And that's going to allow me to start the ingestion process again. It gives me a few options. Do I want to ingest from the last time I stopped? Or do I just want the events from now onwards? I'm just going to select from now and then press continue. And then once all of the streams are up and running, you should see active, all these sections here, right? Active, active. And that means essentially your event stream is up and running and you're successfully streaming from source to destination. All right, so previously we looked at the group by transformation at a high level, and I explained, about window lengths and calculating aggregates over these windows and that kind of thing. But it's worth a deeper look, a deeper understanding on how these things work. Obviously, when you're talking about batch data and you're talking about a group by statement in T-SQL, for example, your data is fixed, right? Whatever you are grouping by doesn't change over time. Whereas in an event stream, you're always streaming new data in. So if we want to perform some sort of aggregate, like a sum or a max, well, we need to know over what time period you're talking about, which is defined as this window. So there's a few different ways that we can create these windows in time based on an incoming stream. And the way that I would categorize them is by, does the window have a fixed length, or is it variable when we're thinking about which is the right window to choose? And do the windows overlap, or do they not overlap at all? So I've built this grid here, and now let's look at some of the different options we have for designing our windows. So the first one, and the most basic one, is the tumbling window, which is categorized by having fixed window length and non-overlapping windows, right? So we can have a window length of 1 minute, for example. So each window will be 1 minute and they'll start one after the other, but they won't overlap. So an example of a tumbling window aggregation that we might make would be, okay, each hour I want to calculate the average air temperature in my living room at home, right? So that by the end of the day, you'll have 24 readings of what the average air temperature was for each hour in the day. That's an example of a tumbling window aggregation and group by that we could perform in an event stream. The next one to draw your attention to would be the hopping window. So that's very similar to the tumbling window, but the windows in this instance can overlap. So we've entered this axis, the overlapping windows. It's still going to be a fixed length. So if we continue the example that we had about the air temperature in our living room, we've still got 1 hour windows here, but this time the windows are overlapping, right? So maybe every 30 minutes we start a new window. So obviously in the hopping window example, we're going to get twice as many data points in the output, right? Because now we've changed the hop size. So the hop generally is the distance between the start of the first event and the start of the second event. So this is your hop size of 30 minutes in this example. So now we have twice as much data on the output as this, right? Because we've overlapped them by 30 minutes. Why would that be useful? Well, you're getting a finer grain for your analysis, right? You're getting twice as many data points. It's going to result in more data storage, but it's allowing you to capture data at slightly more fine-grained intervals, so your decision-making cadence can be quicker. So the next window type we're going to be talking about is the sliding window. So for this example of the sliding window this time, we've got a fixed window length still and overlapping windows. And the difference between these two is that the sliding window, it's going to produce windows at every possible interval, right? So there's no defined hop size that we're worrying about here. It's basically going to create lots of windows all the way down, as many as possible, system generated. For that reason, it's important that we normally pair a sliding window with some sort of filter on the back end so that we can answer questions or generate output events, such as, when there are 3 events in the last, window length that meet certain criteria, for example. So if you're a traffic counter and you want to emit events only when the sliding window notices more than 50 cars passing a certain junction in 1 minute. That would be an example of a sliding window. And obviously it's going to slide that window all the way through with all possible combinations every second or millisecond. And then it's going to emit the output events when it meets certain criteria. If you pair it in an event stream, you've got to do this as 2 separate or nodes in your event stream. Pair it with a filter. Otherwise, you're going to get loads and loads of output events because it's doing every single combination or every single possible window. The next one we're going to talk about is the snapshot window, and this is where this categorization with fixed window length and overlapping windows gets a little bit shaky, but I'm going to continue it because we've come this far. So for some sensors, they are going to give you a snapshot of data, but it might be what I would describe as bursty, right? So you get a lump of data and you might want to perform some aggregates over all of the data that is supplied at that snapshot, at that time period. And then you might have to wait for a while, and then they're going to send you more data, and you can do that same snapshot window, right? So it's a single point in time. Some sensors, they just give you bursty data, like more than one event at a time or one reading at a time, but it will all be at the same timestamp, right? So you can perform some aggregates over everything that you get in that snapshot. They're not going to be overlapping because this is done by the timestamp that it's received in the system or the timestamp in the data itself, but they're not going to be overlapping. It's just going to be a single point in time aggregate. The last one that I want to talk about is the session window. So this time there's going to be non-overlapping windows, and the window length this time is variable. So the session window, if you've ever built a website and you've used Google Analytics to track people navigating through your website, this is where the session window comes from, because the session is when someone navigates to your website and then you get some analytics about, oh, they've been to this page, then they go to this page, and maybe they've put something in their cart. And you've got an e-commerce website, and then they go and buy it, and then they close down the tab, or they navigate to a different website, and that's the session finished. So the window length, aka the length of your session, is variable. Bringing that into the Fabric Eventstream context, what it's going to do is it's going to group your data, your events that are incoming, based on locality, right? Based on when they arrive. So if you don't receive any data for an hour, well, you won't get any output events come through. All right, so that's just a high-level categorization and explanation of these 5 window types that you can expect to find in an event stream group by transformation. Now let's take a look at some of these in action. All right, so here I am in the second event stream that we're going to talk through today. This one is RT004, and we're going to be exploring specifically group bys and aggregations and different window functions, what they mean and how to configure them in an event stream. So let's switch from live mode for this event stream back into the edit mode, and let's explore this one. So for this event stream, we've used a different source. We're using the yellow taxi sample data set here. This time it's a high data rate sample. So if you're on your own capacity, just beware of that, right? This is going to be ingesting more data and it's going to be using more capacity units. But if you're on the trial, happy days. All right, so from the source, this is going to be the start of our event stream here, RT004, that's the name of our event stream. Now this time, again, we're going straight into a managed fields. Typical to use a managed fields early doors to get the data types in order. The reason why that's important, especially with aggregations, right? If we click into what this managed fields is doing, this time we've had to change the types. Okay, so it's come in as a string, this particular field, and this is the vendor ID, so it's the unique ID for that particular data set. We're converting from a string into an int. Okay, now for the ID, it's not as important, but what it is important for is things like fair amount. So again, that's come in as a string. We're converting that to a double. The reason is because we want to perform some sort of aggregation on this column. Same with passenger count. So it's not possible to perform like average, min, max when your data is coming in as a string, right? So it's very common to have your managed fields to get your data types in order to allow for the downstream group bys and aggregations to actually work. So if you start doing a group by, for example, and you notice that it doesn't have any available columns for you to perform an aggregation on, it's probably because you haven't converted those data types correctly. All right, so what have we got then? So downstream from our managed fields, here we've got 3 different group bys. Okay, we've got a hopping window, a tumbling window, and a sliding window. So these are the first 3 that we looked at on our slide. Let's look at how we can configure them, what they look like, what the output looks like, right? So we'll start with the hop. So let's click on select here. What are we doing here? So the way that we configure a group by transformation in an event stream, there's 3 main components, right? There's the aggregation. So what's the numeric thing that we're actually trying to calculate here, right? Now, I've already done this one as the sum of the fair amounts, but we could equally do a variety of different aggregations, average, count, min, max, standard deviation, good quality testing, variance, that kind of thing as well. And we need a field. So that's what I was mentioning before. If you don't see any fields in here, it means that you need to get your data types in order first. So I'm just doing the sum of the fair amount because that's what I want to do. So that's the first thing that we need to configure. It's our aggregation. Then we have the group by. So this is optional. We don't necessarily have to do a group by, but in this example, I want to know the sum of the fair amounts for each vendor ID. Okay, so that's what I'm interested in. And then the important bit, the time window, right? So I want to do a hopping window. These are the different things that we looked at, the options here. If you remember, the hopping window was a fixed window length, and we also have to define the hop, right? Which is the distance between the start of the first window and the start of the second window. And they must overlap those windows. So that makes sense when you look at the different configuration options. We need to specify the duration, which is the window size. So in this example, I've got a 60-second window size with a 30-second hop size. So what that essentially means is we're going to do 60 seconds window length, and then we're going to do, after 30 seconds, we're going to start the second window like this, and then 30 seconds again like this. So this is the hop size, and that's basically how we can configure the hopping window. The tumbling window is defined fairly similarly, but we don't have the hop size, right? So this time we just have the window length, which is 1 minute, 60 seconds in this example. And we know that because we've defined it as a tumbling window, it's going to do this, and then this, and then this, and then this, obviously with equal window lengths. Just my drawing is quite bad, but you get the picture. So it's very simple to configure. If you're wondering what this offset parameter is, essentially what that means is the tumbling window is inclusive in the end of the window and exclusive at the beginning, right? So the offset can be used to change this behavior a bit. So you might want to use the offset parameter to include events at the beginning because it's exclusive at the beginning. So it's not going to take ones that fall directly on the start of the window, but they're inclusive at the end. Okay, so it's going to get those. So the 1 second offset, for example, just shift that slightly to include events that happen right on the start of the window. Finally, we've got a group by sliding. So let's have a look at this one. So the sliding window is you're going to define a fixed window length here. This time it's duration of 10 seconds. And it's essentially going to slide that 10-second window across every possible start and end point of that window. And it's going to calculate whatever aggregation that you've specified. In this example, I'm counting the number of rows, right? So the number of rows that happen at every timestamp. That's why it's useful to pair it with a filter in the event stream. And we can do that to say, okay, I want you to output an event into my destination here only when this count is greater than 300, right? So when we have more than 300 events, remember these are taxi journeys. So maybe you have more than 300 taxi journeys in a 10-second period across the city, and that might trigger some sort of categorization as peak time, right? You've got so many taxis currently, more than 300 in a 10-second window, so that might be, we need to up the prices if you're Uber, for example. Then we have the destinations of these event streams. So we've seen this before, but I'll just show you this one again. So here we've got some of the fares. We're saying that it's a 30-second hop with 1 minute window size, and we're streaming it directly into this KQL database and this KQL table name. And it's the same for all of these. Again, when we're happy with it, we can switch it back to live. We didn't actually change anything, so it's already set up. All right, so that's a quick look at group bys, transformations in an event stream. Let's head back to the slides. All right, so we're making good progress through this map of Fabric real-time intelligence. We've looked at the event stream, but now let's look at the alternative that we have for ingesting streaming data, and that is Spark structured streaming. So as you know, Fabric Spark is an implementation of the open source version of Spark. As such, we can use Spark structured streaming, which is simply a part of Spark, in Microsoft Fabric. Now, the way that Spark structured streaming works, it's actually designed in a very clever way, because it essentially breaks up an incoming data stream into what they call an unbounded table, right? So new data in the data stream is essentially converted into new rows, appended into this unbounded table. So it just goes on forever and ever and ever. Now, why this is so cleverly designed is that these unbounded tables, they are built on top of the Spark SQL API in Spark. So the code that you write is very similar for Spark structured streaming to what you might be familiar with, writing stuff with the data frame API, PySpark, for example, in the batch world. In fact, it's a common development process to start off just figuring out your code and your transformations that you want to perform in the batch scenario. Then you can quite easily change your code to fit with Spark structured streaming. So this is a very simple piece of Spark structured streaming code from the Microsoft documentation. Now, hopefully this looks familiar to you, right? So we're now, instead of doing spark.read, we're doing spark.read stream, and we're passing in this configuration for an event hub. This is an Azure Event Hub. So if you're using Azure Event Hubs as a source, Spark Structured Streaming integrates very well with that source. Then we're defining the schema as such, which looks very similar. You should be familiar with the Spark schema definition. And then what we can do is do df.writeStream here, including all of these different with column, just changing the data structure slightly of that stream before doing df.writeStream. So read stream and write stream, they're the key components of a Spark Structured Streaming implementation. So let's talk about when you might choose an event stream and when you might want to choose Spark Structured Streaming. Well, obviously the event stream, as we've seen, is completely no code. So that's one of the major benefits or selling points of the event stream, is that anyone really can build an event stream. It's low code, it's very simple, easy to learn, and easy to manage. Now, if you're streaming from one of these supported sources, we went through those, whether it's Azure Event Hub, IoT Hub, or the CDC sources, Change Data Capture, or custom endpoint, or third party like Kafka, Kinesis, that kind of thing, then you might want to consider Eventstream. Now, you can also stream some of those sources into Apache Spark Structured Streaming as well. You also might want to choose an event stream when you don't have to do much complex transformation, right? We've looked at the transformations there. It's fairly basic, things like filtering, things like changing the data types, some group by transformations, that kind of stuff. But anything past that is probably going to be better suited with Spark Structured Streaming. And event streams are better integrated into Fabric. So you can write to a variety of different Fabric items, including the Lakehouse. So as you'll see, you can write to a Lakehouse from Spark Structured Streaming as well. But the other ones are unique. KQL Database, we can also write to with an event stream. Activator, also another event stream, like derived streams as well. So having said that, when might Spark Structured Streaming be a better decision? Well, if you're already using Spark for your data engineering, then as we mentioned, the way that Spark Structured Streaming is designed, it makes it fairly straightforward to convert batch data engineering jobs into streaming jobs. It's a pro code approach, which for many is a benefit, right? It enables you to do things like unit testing to improve reliability. You can do more complex stream transformations, more complex windowing as well. Obviously, if you've already got existing Spark Structured Streaming code from other data platforms, then you're definitely going to be choosing Spark Structured Streaming in Fabric as well. And if you want to just directly stream into a Lakehouse and you don't want to have to worry about the real-time experience at all, it gives you that option. Now, that's not to say that you have to keep it in that Lakehouse, right? You could shortcut it from that Lakehouse into a KQL database. So if you wanted to kind of get the best of both worlds, in my opinion, the really strong point about the real-time experience in Fabric is the KQL language, and you don't necessarily have to use an event stream to take advantage of that. So we've talked about ingestion via the event stream and also Spark Structured Streaming now. In the next section, I want to talk through storage and analysis using KQL, the KQL database, and the Kusto Query Language itself. So you might have heard that the DP-700, there's lots and lots of KQL. That's what people say. And there is more than there is in the DP-600, right? So again, I would recommend that you're familiar with the following topics, things like the Eventhouse, KQL Database, KQL, things like the basics, filtering, joins, window functions, because they have their own windows in KQL, management commands, and then monitoring and optimization of KQL queries as well. Rather than just talk about this stuff, let's head over to Fabric. And we're going to start with a tour of the Eventhouse, look at the key features, and then the KQL database. And then we're going to go through lots and lots of different examples of the KQL language in action. All right, so let's start with a bit of an overview of the Eventhouse UI. Then we're going to look at the KQL database UI and how that's structured. And then we're going to dig into some KQL queries and explore that language in quite some detail. So this is the homepage of an Eventhouse. This is what it looks like. Now, the Eventhouse you can think of as a collection of KQL databases. On its own, doesn't really represent much. It's just a grouping of KQL databases. Hence why we can have this big plus button for creating a new database in our Eventhouse. We can perform things like minimum consumption or change that setting in here. Essentially what that means is you can offer some control over how much your Eventhouse is going to consume in terms of capacity units at the minimum level. Currently I've got on demand. We've also got some plugins for Python language extension. I think this is new. I haven't actually explored this in much detail yet, but it does look quite interesting. Maybe we'll do a video on that in the future. Then we've got these details on the right hand side. So you can see what region I'm currently in, the query URI and the ingestion URI. So if you're using the Fabric REST APIs, then they'll be useful to know about because you can use those to ingest data into, for example, the ingestion URI. We can see the consumption method that we just looked at. We don't have the Python plugin installed. Then we have the system overview. So we can see the size and the compressed size, ballpark figure of how much data we have in total in the Eventhouse. If we scroll down, we can see some activity, right? So we've got various levels of ingestion going into this Eventhouse. Now I've only got one database, as you can see down here in my Eventhouse here. If we click on databases, you get a bit of a summary card of what's happening in all of my databases. As I mentioned, I've only got one, so it's not very interesting to look at. And we've got monitoring. We're going to be looking at the monitoring of event houses and KQL databases and KQL queries in a future video in this series, because monitoring is a key part of the DP-700. So that's pretty much all we have at the Eventhouse layer. Now let's dig into our KQL database and explore that in more detail. All right, so there's a bit more to look at now. So now we're at the KQL database level, and you can see lots of interesting options. We can create new items, new KQL tables, materialize views, functions, update policies, and also we can bring in data from other areas in one lake, like a lakehouse table. Maybe you've got a reference table, like a dimension table of your sensors, right? So where they're located, what the brand name is, when they need to be maintained, for example. That sort of stuff would be great to bring in as a shortcut, and then you can reference it in your KQL queries. Get data is going to be via any of these supported sources. We can also start querying the data in our KQL tables with KQL code. Obviously, we'll be looking at that very shortly. We can add new items like a KQL query set, a dashboard, or a notebook as well. We can also look at the data retention policies here. If we click on data policies, we can see two things. We've got retention and caching. Here we can specify different policies for keeping our data. Again, here we're talking about real-time systems. So sometimes you only want to store or retain your data for maybe a month. If nothing bad happens over that period, maybe this is log files, maybe you're ingesting directly into the lakehouse as well for perhaps like cold storage. So you want to delete it from the Eventhouse, the KQL database, after 30 days, for example. Currently, I don't have that policy set. I'm just on unlimited, so it's not going to delete. We've also got caching as well. So we have this concept of a hot cache and a cold cache. So by default, what's happening here is I'm storing my data in this hot cache in an unlimited fashion, right? Which is going to cost more, but it's going to help with query performance. So if you don't want all of your data to be stored in this hot cache, like in local SSD, then you can turn that off and it's going to save you some money. Down the right-hand side, we get these details about this specific database that we're in. We can look at the data storage. Again, I don't know why that's particularly useful, apart from understanding that that's how much you're going to get charged for. The compressed version here, 154 megabytes, which is good to know. Then we have the OneLake integration button. What that means is it's going to be the default value or the default setting for all of your tables in your KQL database. Here I've set it to on, right? You can actually turn this off at the individual table level as well. If you right click on the right hand side where you see tables, you can change the OneLake availability to off for that specific table as well. Now that we're over on the left hand side, might as well explore that area in a bit more detail. So here we have our RT001, which is the name of our KQL database. You'll see the relevant KQL query sets that are related to that particular database. Now, the query set can actually live outside of a KQL database. For example, if I go back to my workspace, you'll see in here, in the real-time folder I've got here, these are KQL query sets. They query data in this KQL database, but this is like the default query set here attached to this Eventhouse, but it doesn't necessarily have to be that way. So now we're back in our KQL database on our quick tour, and we've got tables. These are all of the tables that I've streamed in from my event stream here. We've also got some shortcuts. So I've shortcutted in some data from a lakehouse that I want to use in some of my KQL queries as well. I've got some materialized views here that I've created on my data, and we've got a function here that we'll explore when we look at management functions and some streams. Okay, so that is a quick tour of everything available to you in a KQL database other than the querying. So now let's dive over into some code and look at how we can query data in a KQL table with the Kusto Query Language. All right, so next up, we're going to be doing a bit of a deep dive on KQL. So I've got 4 different KQL query sets here. I've got some basics, so we'll start off pretty basic and we'll go through some of those. Then we'll look at a load of different filtering methods available to us in the KQL language. Then we'll look at different aggregations that we can perform in KQL this time. And then we'll look at some management commands. This is for things like creating tables, creating materialized views, things to actually do stuff to change the structure of the database normally. So let's start off with some basics. So let's talk about the UI first, what this looks like, how this works. If I just zoom out a little bit, see the UI is not particularly responsive. So as you can see, normally when we're creating KQL queries, we've got our tables available to us down here. We can also bring in things like shortcuts, materialized views. This is our canvas where we're writing our queries like so. Then we've also got the big run button, which is one way of running our queries in KQL, and then some other buttons along the top, if we want to put them into a dashboard or things like that. We're not going to be looking at too much detail into those. So let me just zoom in a little bit just so that you can read the code a bit more easily. So let's start with, how do you actually run a KQL script? Well, the starting point for most KQL queries is a table, right? A table name. So one of my tables here is raw bikes. That was one of the direct ingestion tables that I got from my event stream. If we want to just visualize, see what that looks like, lots of different ways that we can do that. Either we can select the table name, like drag our cursor across all of that and either click run, or we can do shift enter like so. Or if we're doing shift enter, we can just have the cursor somewhere in the name of the table and do shift cursor like so. Now this, because we haven't done anything with it, it's going to bring us back the records from the table like so. We get this nice preview of the data here. If you've got a very large table, I think it caps out at maybe 50,000 records. If your table is bigger than that, it's not going to visualize absolutely all of them. And it shows you the tables that you've got here. You can sort these, do this sort of thing, grouping by. So you can do some pretty interesting stuff within the UI itself. You can also look at the stats for that particular query, which is useful once we get to query optimization. It tells you how much of it is coming from the hot cache, the cold cache, that sort of thing. Everything's in the hot cache because that's the policy that I've set in this KQL database, but useful to know. All right, so let's go through some of the basics of the KQL language. So probably one of the most important defining features is this pipe operator. So the way that this works is we start with a table at the top and then we do stuff to that data set. So in this example, if we use this pipe operator, what that's going to mean is that we're going to take everything from line 1 of our query, pipe it into line 2, and we're going to do whatever's on line 2. In this case, we're talking about a count. So we're going to count the number of rows in raw bikes. If we run this, we're going to see a count of 5,104, like so. So now after the counts, the next one that I want to look at is raw bikes. And this time we're going to do take. So take is another operator. And essentially what it's going to do is sample data from that table and return 100 values. Right, so these are not necessarily the top 100 values. These are just any 100 values from this data set. So again, if we do shift and enter, this time we're getting back 100 records in here from this data set. Next up, what we can do is we can combine the take operator and our count. So if I showed you this, what would you expect to be the output here? Because remember, we're chaining our raw tables, then we're doing take 100 on it, and then we're doing a count of that. So it's not going to be a count of the original data set, it's going to be of what it is in this state here, which hopefully you've worked out is going to be 100. Next up, let's look at the most recent records. So this time we're using the top operator. We're going to get the top 10 events by ingestion time. Okay. So remember, if we were to just highlight our original table and select that, we don't actually have a timestamp value in this data set, right? So we're going to have to use the ingestion time, which is kind of like the built-in property for when that data got ingested into the system. And we're going to do it by ingestion time descending and the top 10. So we'll get the most recent events in this table. Next, let's look at being a bit more selective about the data that gets returned. So we're going to build upon iteratively that first line. So we're going to keep top 10 by ingestion time descending, but we only want the bike point ID, the number of bikes, and the number of empty docks, right? We don't really care about the street and the neighborhood and the latitude and longitude. We can get all that maybe from some metadata table or reference table. So we only care about these tables, so we can use the project operator, right? That is going to allow us to select the columns that we care about. Run this one. This is what it looks like. Now we can also add new calculated columns onto our data set. Now you can actually use project for that as well, but we can use extend is the name of another operator. Again, we've chained it on to the end of our query. So we're kind of going through various stages in our analysis or transformation steps here. But the extend allows us to create new columns. So we're defining a new column called ingestion timestamp here, and we're defining it as the ingestion time function here, which is the built-in timestamp for the time that that event or each event was ingested. So let's run this. Here we go. That's what that looks like. Next up, let's look at sorting. So again, we're building on this same thing, but we're adding a sorting onto the end here. We're sorting by the bike point ID. Now you'll notice that here we're passing in ASC, so ascending. So by default, sorting in KQL is descending, right? That's going to be the default order. So when you call sort by bike ID, for example, without ascending, just like this, it's going to look like this. So it's going to go descending like this from high to low. Now these are string values, but it still works the same. So if we want to do, from low to high, then we need to specify ascending like so. All right, so that's just to get us started with the KQL language. Now let's move on to some of the filtering functions that are available to us in KQL. Okay, so let's continue with our raw bikes. And this time I'm going to introduce you to the where operator, which is how we're going to do our filtering, right? In this example, we're starting with some string filtering. So here, where the neighborhood is equal to mile end, you'll notice that the equality operator is 2 equal signs. Now what that means is that it's case sensitive. So it needs to match exactly the case of what we're searching for here. We'll look at KQL optimizations and best practices, but this is going to be more efficient than running a similar query with the case insensitive equality operator, which is this one here, right? The equal sign with the squiggly tilde, I think it's called. Yes, sometimes we might need that, right? If you're not 100% sure on the case of what you're searching for, you need it and you might just suffer the lack in performance, but know that it's always best to specify the case-sensitive version if you can. But we'll look more at optimizations and best practices in a future week. Next, let's look at string has and string contains here, so 3 and 4. Now, on the surface of things, these are fairly similar, but there are some subtle differences. Has is going to search for the entire term. So the way that KQL works and how it's indexed is that if we just run this as an example, just to get this data, the way that KQL works is it splits all of your string variables into different what we call terms, right? So this would be 3 terms, worlds, end, place. And what has is doing is checking if what you put in there is a whole term. So it's returning end is a whole term, right? So it's not going to check for if these END exists anywhere in the string, right? It has to be a separate term. And you'll notice that the has 191 records, whereas if we run contains, we're going to get more records. So it's 286 records for contains, because what contains is also the results where, it's not an individual term. Stevendale Road would be an example of where contains would return a result, but has would not pick this up because END, right, end, exists within a different term. So the term here is Stevendale, so it would be returned for contains, but not for has. Because of that, has is more efficient, right? But sometimes you want to look for individual, substrings as well within a text. So they have use cases for both of them. Has is more efficient, obviously, because you're searching for the whole terms, and that's how it gets indexed in the KQL database. But know that both of them have their uses. Then we've got things like starts with, just the classic operations that you can do with strings in most query languages. We've also got ends with. So this time we're looking for all of the byte point IDs that end with 649, like so, as well as the equality operator. We have not equal, so we can put an exclamation mark in front of our equal sign, like so. So where the neighborhood is not in the West End, like so. So here we're going to get everything that's not in this West End neighborhood. So Chelsea, 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 for example. Next, let's look at some numeric filtering. So that was string filtering. Let's look at numeric, right? Similarly, we can do some equality. So where the number of bytes is equal to 0. We can also do less than and equal to, more than and equal to, that kind of thing. Classic numeric filtering. This one we're doing raw bytes where the number of empty docs is greater than 30, for example. So there's lots of space. Maybe you want to relocate some bytes from these docs into some of the empty ones. We can also do ranges. Right, so the way that we would declare a range within KQL, where the latitude, here we're using the keyword between, we're doing our start range, then we do these two dots here, and then the end range here. So I'm looking for events that fall at the latitude of between these two values, like so. Next up, let's look at datetime filtering. Right, so KQL, it is the engine of time series data, right? So there's a lot of built-in datetime filtering and functions that can help us do these sorts of time-based analyses. So let's look at some of those now. So raw bytes, where the ingestion time is equal to a specific date time, very precise, but you might want to do that. We can also use less than and equal to, more than and equal to, that kind of thing for after a specific date range. So show me all the events that were ingested in this example after this specific date, or before, for example. Then we can start looking at some of these keywords. So we have where the ingestion time is greater than 24 hours ago. So what that means is within the last 24 hours. So that's useful. We can also go a bit further and say, okay, show me all the events where the ingestion time was between 24 hours ago and now. Okay, so it's going to return similar results to this, but this time we're showing you the now operator there. And what about records ingested yesterday? Well, again, we're going to do between, but we're going to do start of the day 1 day ago and the end of the day 1 day ago. So all of the events that were ingested yesterday into this specific table. I think I turned off this event stream, so there's nothing happened yesterday. We can also do combinations of filtering. So multiple conditions with and. So where the neighborhood is mile end and the number of bytes is greater than 5 in this example. Or condition, as you'd expect, either it's in mile end or they've got a number of bytes greater than 5 in this example. We can also use the in operator, similar to T-SQL, where we want to check for membership of a list. So return only the events that happened in the neighborhood of mile end or sans end. That's where we get that. And for most of these queries, we can do where not. So negating the filter that we want to specify. So if we carry on this example from the one above, where not the neighborhood is in mile end or sans end. So show me everything that's not from these two neighborhoods, like so. All right, so that was filtering. Now let's look at summarize and aggregations in KQL. So again, we're continuing with the raw bytes data set. And when we want to do some sort of aggregation in KQL, we're going to need the summarize operator, and we can use the summarize operator to do things like counts and mins and max and all your standard aggregations. So if we run this one, we're going to get an aggregate of the count of all the records. Now in this example, I'm not using a group by column, but our second example here, if I was just to run these top two lines, what you'll see is I've added the by byte point. So now you'll get the count of events, the number of events, for each byte point in that table. Then we can sort by total events. Maybe you want to see which bike points have the most events. And finally, I just want the top one. So which of my bike points has the most events? That's essentially what this query is telling us. And you can see the iterative way that we can create progressively more interesting queries, right? Step by step. We can also perform multiple aggregate calculations. We don't just have to do one. So in this example, we're getting the count again, the total events, but also the minimum amount of bikes, and we're doing the group by of the bike ID, like so. In this query, we are doing the total events of empty stations, right? So how many events were there where the number of bikes were 0? And we're using count if. So essentially it's similar to count, but it's a conditional count. So it's only going to count that particular event if it matches this condition, and the condition is number of bikes equals 0. Again, we're doing it by bike point. So this might be useful if we want to know, okay, which of our bike points in the city frequently run out of bikes, right? So say, for example, here, we got the total events here and the total events empty stations. So in our data set, 293 has this total events empty station of 0. What that means is that there are no events for that bike point ID where there's been an empty station. So that's good. But if we scroll down, this one, so what's this one? 679, there's been 21 instances or 21 events where this bike point has been empty. So that's maybe something they need to change in how they move bikes around the city to add more capacity into that station, for example. Then we can do more complex things like adding percentages and things like that. So in this example, if I just run it, what we're doing is, well, we're going to keep our total events. We're going to keep our empty stations, our total events of empty stations, like so. Now we're going to do an extend, and we're going to do the empty station percentage. So we're going to look at dividing these two. In KQL, you have to, if you want to use this division operator, you need to be casting them into a double, essentially. So we're going to do, okay, how many events were there where the station was empty versus all the events, and round it. So what we can see is 0. So this one is 41% are 679. So 41% of the time out of all the total events here was this station empty. And, again, we can progressively add more and more interesting stuff into our query. So we want to filter the percentage where it's not equal to 0, because we care about the stations where bikes are running out, right? So interestingly, this reveals that bike points 531, there's 52 events in the data set, and every single time it's empty, right? So that's not a particularly good thing. Maybe it's out for maintenance or service or something, but it's useful to dig that information up through this summarize analysis. So in this example, what we're doing is we're summarizing, again, we're getting the count of events, but this time we're constructing bins, right? So groups of 12 minutes is our bin length. And so we're saying how many events were there every 12 minutes? And you'll see that these are different bins of our data going up in 12-minute intervals. And we've got 404, 470, 470, 468. So it's telling us how many events are we getting every 12 minutes, essentially. And we can do similar by adding in the bike point here. Okay, so we're just adding more granularity into that aggregation. So now we're doing it by the bin, and the bike point ID here. So for each bike point ID, how many events were there in this period? So in this first bin, we've got 3 events each, it looks like. So we've got a 12-minute bin size, 3 events in there. So roughly we're getting data for each bike point. Every 3 or 4 minutes, we're getting new data, new events from each bike point. All right, so let's move on to management commands. So management commands in KQL are slightly distinct from what we've looked at so far in terms of the query language. You can spot a management command most easily because it has this dot at the start. So all of the management commands that we're going to look at have this dot. Now, let's look at a few common ones. Let's start with show tables, so dot show tables. We can use that to bring up a list of the tables that exist in the current KQL database. So these are all of our tables in here, and we can explore them. All right, so the second management command that we have here is create table. So we're going to specify the name of the table, then the columns in the table with a colon to the data types here. So I'm creating a table, and it's got 3 columns: student ID, exam score, exam code, right? And the GUID, so these are the data types, so the GUID, the int, and the string. So this table already existed, but if I delete this table, like so, now you could do that with a management command. We'll see that in a second. But if I was to create this table again, and there we see it. So there it was created like so. What we can also do is ingest inline, right? So if we only want a few different records into our table, or we can use this management command for ingesting data from a data pipeline, right? Hopefully you've noticed that there is a KQL query script from a data pipeline. So if you want to do logging from your data pipeline, you can use this sort of syntax to ingest a log into a KQL table from a data pipeline. Pretty cool. All this looks like is ingest inline into table, name of the table. Then we have this interesting syntax here. And then you just do the lines that you want to ingest. Looks a bit like this. We're going to get a bit of a log. Has errors, is false, which is good. If we just query this, see what it looks like. So we've created this table with a management command and we've ingested some data into it with the management command. Here we can see that our students are taking the DP-700 and they've all passed. Happy days. So we can also do clear data, clear table, and you'll notice that it's going to throw an error. It's probably because of the OneLake setting. Let's scroll down to have a look at the error message. Essentially, you can't clear the data in the table if you've got OneLake availability on for that table here. Now, because I've got it as the default of on, when I created the table, it automatically gave it that permission. So what I can do is if I go back to the database, bear with me 1 second, rather than the actual query set here, and we'll dig into real time. We'll go into the KQL database here. If I change this OneLake availability to off for this table, it's going to allow me, if I go back to my query, now I should be able to clear this table like so. So when you've got OneLake availability turned on for a particular table, it doesn't like you clearing data out of it, essentially. So now if I rerun this, we can see that we don't have any data in that table again. The next one is materialized views. So materialized views allow us to materialize, essentially, to write into the actual table, into a new table, the output of a summarize statement in KQL. There are a few different options that we can specify, most importantly being a backfill. So when we want to materialize this view, do we want to do it from this point onwards, i.e. backfill equals false, or do we want it for all data in the table as it already exists, the historic data as well? We can do that with backfill equals true. So let me just create this. I think it probably already exists. So it's not going to like that because I've already created that particular materialized view. So if I come down here, I can see it's this one here. What we can do is .drop materialized view. The name of it is this one here. Just show you another management command here. So now I've dropped that materialized view. It's going to give me an error because it doesn't exist anymore. And now I can recreate it like so. So essentially the important things to bear in mind with this is the name of it. These are just the kind of like the properties in between these brackets. I want it to be effective from this particular date, this materialized view, on the table raw bikes, and then the raw bikes is going to be what you build your summarize query on top of. Now you might think, how do materialized views work in a real-time environment, right? If you've ever used materialized views in Postgres, for example, or Synapse is another example, well, it makes sense in a batch scenario, right? Because you're writing the outputs of a view into its own table to improve query performance. In a real-time scenario, the way it works is it splits it into two, right? So at the time you create the view, it materializes that data into a table, and then it maintains what they call a delta, right, of all the data that changes from when you materialize it to when you query it. So it improves query speed by only having to calculate the delta at query time. So that's materialized views creation. Now another thing we can do and use in our KQL environments in Fabric is creating functions. So that's the next management command that we can use. And a function works similarly to a stored procedure in T-SQL language, right? We can give it some parameters. Here I'm defining a function called getBikeData by ID, right? So I want to pass in a particular ID and I want to return all of the data points for that particular bike point ID. Not particularly interesting, but does a job. So now we define that function like so, and I can call it like this. So I can call my getBikeData by ID, pass in a bike point ID like so, and it's going to show me all of the events for that particular breakpoint ID. So that gets stored in my functions down here. And that's really handy because I can then use that all throughout my KQL query landscape. You can build up some quite complex functions and just use them really easily, like so. All right, so that's a whistle-stop tour of the KQL language. Now, I would recommend that you also have a look at window functions for the exam. KQL have their own window functions separate from what we looked at in the event stream. So I'd recommend, if we go on KQL window, make sure you're familiar with the documentation page, all of these window functions here. Let's head back to the slides. Okay, so I just want to finish this video today. We've covered a lot of ground here, but I just want to talk about streaming architectures that exist in Microsoft Fabric and talk about some of the key features. And I'm hoping that this will bring together everything that we've learned today around event streams and KQL and all of that good stuff. So what I've done is I've taken two sample architectures from the documentation, and I'm going to use these and talk about them, talk about their structure and how they work and how you might implement them in your business. So the first one is coming from pretty much the homepage of real-time intelligence. So when you go to the documentation, this is the first image that you see, and it does a really good job of simplifying how all of these things are connected. Firstly, let's talk about the data sources here. So here we've got some of the CDC sources like Cosmos DB, Azure SQL, these kind of things. So if you want to stream updates from your relational database, Azure SQL, for example, into Fabric, that's going to be your first step. Also got things like Kinesis here, I believe that logo is, and Google Cloud Storage as well. So in this architecture, we're using our event stream as our ingestion tool. And then from there, what we're doing is writing to the Eventhouse. So we looked at the Eventhouse, and within a KQL database, within that Eventhouse, we can generate KQL query sets, and then we can use those, we can visualize the output of them in real-time dashboards. Another visualization option that we have available to us is Power BI, of course, and Activator, right? So under this visualize and act section. So we have different options available to us if you're a data visualization specialist. Now, of course, real-time here has a slightly different catalog. Rather than the OneLake catalog, they have their own real-time hub. And in this representation of the architecture, we've got this OneLake. Now, as you know, by default, files in your KQL databases, in your Eventhouse, are not replicated into OneLake itself. So that is an optional thing that you have to enable if you want your KQL tables to be replicated into OneLake so that you can use them across different experiences. That is an optional thing that you can select. Okay, so let's talk about streaming architecture 2, because this one is a bit more interesting. So again, this comes from this architecture Medallion real-time intelligence piece of documentation. And you'll notice that we have a streaming architecture, but it's built across this concept of the Medallion architecture, right? So we have bronze, silver, gold, and then some sort of visualization, action stage right at the end. So here we've got some different sources. We've got Azure IoT Hub. We've also got other event streams and some other things like data pipelines. So I think this architecture is fairly loosely drawn, let's say, rather than highly accurate. But what we've got here is an event house here with some raw table. And we've also got an event stream here that I guess ingests data into this raw table. But what's quite interesting here is that now we have this update policy. I haven't really spoken much about KQL table update policies, probably a bit outside the scope of what's expected in the DP-700 exam. But essentially what an update policy is, it enables us to propagate changes from one table into another table. Right, so essentially what you're doing is you're setting up this update policy on this table here. And then when new data is written into that table, because we've got this update policy, it will then update this telemetry cleaned. I think that's what the suggestion of what's happening here by this architectural diagram. Then we've got this materialized view. So we're going to build a materialized view from the data in cleaned here. And we're going to write it, because we're materializing the output of this summarized query into this telemetry deduped. So that is going to be the next layer in our architecture. And again, we're going to continue this materialized view, use that feature to generate aggregates here. And then latest value view is another gold layer materialized view that we can generate. And then we're going to use those as the basis of our visualizations, either for Power BI or real-time dashboarding, or perhaps we want to do some sort of condition-based monitoring of the data in those materialized views. We can do that as well. Now, from what's shown here, the data in the silver layer is mirrored into OneLake, right? So they haven't chosen to do that for the bronze layer or the gold layer, but the silver layer, just by my interpretation of this architecture, is mirrored into OneLake. If you're wanting to do any sort of machine learning prediction based on that data, that might be a reason why you want to mirror the silver layer into OneLake, because you want your data scientists to shortcut these tables into their lakehouse so that they can perform some sort of inference on that data. All right, so that brings us to the end of this video on streaming and real-time and KQL in Fabric. Now, I do just want to stop here for 1 second and say, if you haven't joined DP-700 Bootcamp in Fabric Dojo, then now is a really good time. So if you're not familiar with Fabric Dojo in general, we've got a massive community here with updates every single day, very active community here, people discussing best practices and the solutions that they're building in Fabric. And inside the classroom, we have our DP-700 Bootcamp. This goes alongside all of our tutorials. So in Fabric Dojo in general, it has over 100 hands-on tutorials to help you master Microsoft Fabric, specifically data engineering elements of Microsoft Fabric. So we talk about data factory, data warehousing, CI/CD, lakehouses, real-time streaming, data quality as well, security and administration, all of that stuff. But inside the bootcamp here, you'll see advice from people that have passed in the community. We've got lots of people that have passed recently in the community. Plus, we've got all of the live sessions. So we've been doing live sessions every week for the last 8 weeks. So you can come in here and, we go into more detail, right? So this was the one we did about real time. And each of these sessions is an hour or 90 minutes. Okay, so there's lots and lots of different perspectives shared, Q&A sessions going on in there. Plus, we've got the notes. So in every single one of these sections, we've got extensive notes. So if you want access to these notes, then make sure you join up to Fabric Dojo. I'll leave a link down below. That's all we've got time for today. I hope you enjoyed that session, and I hope to see you inside Fabric Dojo. But if not, I'll see you in the next video. We're going to be starting the final third of the study guide, all about monitoring and error handling and optimization of solutions in Microsoft Fabric. So I'll see you there.